So in this question, we are given a water tank, and the water tank is a cuboid, and inside the cuboid are 3 cylinders. Now here I've drawn a cross-section through the water tank, and it doesn't really matter what the shape is. All that matters is the area available for the water. Now, the total cross-sectional area of the cuboid is x, and each of these 3 cylinders has got cross-sectional area y. And so the total base area is x minus 3y. Now we're told that this tank is filled with water, and the depth of the water in total is h. So the volume of the water inside the tank, V, must equal the base area times the height. X minus 3y times h. Now we're given a succession of new scenarios in which the columns are removed from the tank, increasing the base area, and the volume stays the same and the height decreases. This gives us some new equations, which I'll write now. So in the second situation, the volume is still V. One cylinder has been removed, so the base area is now x minus 2y. And the height of the water has dropped from h to h minus 50. Then we remove a second cylinder, and the water level drops by a further 30, so the total drop is 80. And finally, the last cylinder is removed. So the base area is now x, and the height of the water we don't know yet. I'm going to call it W for water. So now we have a load of equations and a load of unknowns, and it's tempting to dive into this with algebra and work out what W is. But I'm going to pause for a second and observe these quantities, x minus 3y, x minus 2y, x minus y, and x, form an arithmetic progression. They have constant difference y. And I think we can use this to find an efficient solution. So here I've rewritten the equations by dividing through by the water heights to make the areas, our arithmetic progression, the subjects of the equations. And I can do this because I know that the water levels are all positive. The water level dropped at some point, so there must be some water in the tank. So the left-hand sides are an arithmetic progression, and so must the right-hand sides be one too. And V is a common factor in all of the terms on the right-hand side, so I can divide by V. A scaled arithmetic progression is still an arithmetic progression. So I can say that these 4 terms, 1 over h, 1 over h minus 50, 1 over h minus 80, and 1 over w form an arithmetic progression. And this means that the differences between successive terms are equal. So I can now write down one equation involving only h. The difference between these 2 terms equals the difference between these 2 terms. Now I can rewrite this slightly to help me. I can add this term to both sides to bring it to this side, and I can add this term to both sides. And now I can clear the denominators, multiply through by h, h minus 50, and h minus 80. So we have what looks like at this point a quadratic equation in h. But there's good news. all of the h squareds will cancel. There is 2h squared on the left and 2h squared on the right. So after multiplying out and simplifying, we find the following equation for h. And we can solve this to find that h is 200. So remember that we had that these four fractions formed an arithmetic progression. But we now know what h is. H is 200. So if I fill in the value of h, these fractions are 1 in 200, 1 in 150, 1 in 120, and 1 over the unknown final water level, w. Because these fractions form an arithmetic progression, I'm going to make all of their denominators the same. So I'll multiply top and bottom here by 3. 3 over 600. This fraction is 4 over 600. This fraction is 5 over 600. And we can see now by inspection that the final fraction, 1 over w, must be 6 over 600, which is 1 in 100. And so the final water level w is 100. Now the question asked for the final drop in water level. The water level drops from 120 to 100, and so the final drop in water level was 20.